Hi everyone. In continuation of our lecture on exact differential equations, we'll be taking two more examples. The first is going to be an initial value problem, while the second one is a regular exact differential equation. So let's take a look at the initial value problem. So we're required to solve the initial value problem cos y sin x plus 1 dx minus sin y cos x dy is equal to 0. Given that the value of y when x is equal to 1 is equal to 2. So this is the condition that makes it an initial value problem because we are given the state of the function or the state of the solution of the differential equation at an initial point, that is when x is equal to 1. So just like we've stated, we are going to be following the steps we have outlined in our previous videos. You can look that up to revise it if you have forgotten about it. So the first step now is to check for the exactness of the differential equation. And in checking for the exactness of the differential equation, we know that we are trying to verify the condition that the partial derivative of m with respect to y is the same thing as the partial derivative of n with respect to x. So now from the equation we have, if we compare our given equation, m dx plus n dy is equal to 0. So we have that our m is equal to cos y sin x plus 1, and our n in this case is equal to sin y cos x. So we have to evaluate dm dy, that is the partial derivative of m with respect to y, and also evaluate dn dx, which is the partial derivative of n with respect to x. So in doing that, we have dm dy to be equal to minus sin y sin x. And this is because when we are finding the partial derivative of m with respect to y, we have to keep x constant. And since we are keeping x constant, any other function in x is also going to be a constant. In this case, that function is sin x. So we are only differentiating the cos y to get minus sin y, which then gives us the derivative of m with respect to y. So we can do the same and find the partial derivative of n with respect to x. And by doing this, holding y constant and invariably sin y, we have our result as minus sin y sin x, because when we differentiate cos x, we are going to be having minus sin x. Can conclude that dm dy is same thing as dn dx, and this is equal to minus sin y sin x. So this confirms that our differential equation is in fact an exact differential equation. So since step 1 is done, we can go ahead to solve step 2. And step 2 is finding the integral of m with respect to x. Recall that our m in this case is cos y sine x plus 1. So to find the integral of m dx, that means we evaluate the integral of cos y sine x plus 1 with respect to x. And by doing this, we are also considering, we are keeping y constant. So when evaluating this, we can just rewrite this as cos y integral of sine x dx plus integral of dx. So you can then evaluate this to give cos y cos x plus x. And that's step 2 taken care of. Can then go ahead to evaluate step 3, which is to find the integral of the terms of n that doesn't contain x or any function in x with respect to y. So in this case, we know that n is equal to minus sine y cos x. If you look at this, there is no one that doesn't have a function in x. So we find the integral of 0 with respect to y. So this gives us 0. But before we continue, let me draw our attention back to something we did before earlier. So we said our n is sine y cos x here. We omitted a negative. So here's me making that correction. So when you differentiate cos x, you're going to have sine x and it's still going to give the same answer. So you just have to correct that negative sign. We can then proceed to step 4 since we've solved for step 3. And step 4 says we should add the results from step 2 and step 3 together. And after doing that, we equate it to a constant c. You could choose any other arbitrary letter for your constants, but I just prefer using c. So in doing that, our results from step 2 is cos y cos x plus x. These are our results from step 2. And our result from step 3 is 0. I'll say is equal to constant. Therefore, we have cos y cos x plus x is equal to c to be our general solution for the differential equation. So since we've been given the initial condition that the value of y when x is equal to 1 is equal to 2, we can substitute this into our original function. Let's call it equation star or asterisk as the case may be, to get our particular solution. So in this case, we want to find c. So we said cos y cos x plus x is equal to c. Now let's substitute x is equal to 1 and y is equal to 2 in this equation. So we have cos 1, sorry, cos 2 cos 1 plus 1 must be equal to c. So in evaluating this and setting our calculator to radian, we are going to be having c to be equal to 0.3579. Kindly do well to confirm this, confirm that you've gotten this on your calculator, and if you haven't gotten it, make sure you get it right before proceeding. So therefore, the particular solution of this differential equation is given as z is equal to cos y cos x plus x, and that's equal to 0.3579. So this gives our general solution, our particular solution for this differential equation. So let's take a look at our final question on exact differential equations before proceeding to other concepts. So we're required to solve 5x raised to the power 4 plus 3x squared y squared minus 2xy cubed dx plus 2x cubed y minus 3x squared y squared minus 5y raised to the power 4 dy to be equal to 0. So this is pretty straightforward, just like our other differential equations. So let's try to solve this. So we need to first check for exactness. So if you compare this with m dx plus n dy, we can see that m will be equal to 5x raised to the power of 4 plus 3x squared y raised to the power of 2 minus 2xy cubed, and n is equal to 2x cubed y minus 3x squared y squared minus 5y raised to the power of 4. The next step is to find the partial derivative of m with respect to y. So since we are going to be keeping x constant, when you differentiate 5x raised to the power of 4 with respect to y, the result is 0. And when you differentiate 3x squared y squared with respect to y, you're going to be having 6x squared y. When you differentiate minus 2xy cubed with respect to y, you're going to be having minus 6xy squared. So the next step is to find the partial derivative of n with respect to x. And with that, we're going to be having 6x squared y minus 6xy squared. When you differentiate minus 5y raised to the power of 4 with respect to x, you're going to be having 0 as a result. And from this, we can see that the m dy is equal to the n dx, showing that this equation is an exact differential equation. So the next step is to integrate m with respect to x. And that's, we're going to be having the integral of 5x raised to the power of 4 plus 3x squared y, x squared y squared minus 2xy raised to the power of 3 dx. Since y is a constant and invariably any function in y, we now have our result as 5x raised to the power 5 divided by 5 plus 3x raised to the power of 3 y squared divided by 3 minus 2x raised to the power of 2 y raised to the power of 3 divided by 2. So this gives us x raised to the power of 5 plus x cubed y squared minus x squared y cubed. So that's step 2 sorted out. We then proceed to step 3, which is to integrate the terms in n or terms of n that doesn't contain, sorry, that doesn't contain x with respect to y. So that means we're going to be, okay, before we do that, let's recall that our n is equal to 2x cubed y minus 3x squared y squared minus 5y raised to the power of 4. So in this case, the only term of n that doesn't contain x is minus 5y raised to the power of 4. I'm going to integrate this with respect to y. So this gives us minus 5y raised to the power of 5 divided by 5. And this gives us minus y raised to the power of 5. So the first step is to add the results from steps 2 and 3 and equate it to a constant. So that means we are going to be having x raised to the power of 5 plus x cubed y squared minus x squared y cubed, which is the result we obtained from step 2, minus y raised to the power of 5, which is equal to c. So our solution to the differential equation is z is equal to x raised to the power of 5 plus x cubed y squared minus x squared y cubed minus y raised to the power of 5 is equal to c. So you can go ahead to do the fifth step, which is to check if the results obtained is a solution of the differential equation or satisfies the differential equation. And don't forget to do this. All we just have to do is find the total differential of z. So with this, we've come to the end of this video. See you guys in the next video.